Bismillahirrahmanirrahim. Assalamualaikum and very good evening to all of you. Welcome back to our class, the BAA 2213, the Reinforced Concrete Design 1. In this video, I will discuss about the example 5.5, which is the design of non-slender column with biaxial bending. Okay, first of all, let's take a look to the page number 200 from our module book, biaxial bending. Okay, the biaxial bending is compulsory to be or necessary, okay, to be checked if, okay, based on these two conditions, A and B. You can refer to your module later, and no further checking is necessary if the slenderness of y axis divided by slenderness to z is lesser or equal to 2, and the slenderness ratio of z-axis divided by slenderness ratio of y-axis is lesser than or equal to 2. And okay, this is the another condition. It must be I mean, all these four requirements. Okay, this is the first requirement, this is the second requirement, this is the third requirement. You must check the EY over HEQ divided by EZ over BEQ. Okay, we can refer later what is the BEQ, what is the HEQ, and this one 4. This is number 4. So 1, 2, 2, 3, and 4. All these 4 situations must be checked if the requirement fulfill all these 4 checking. So no further checking for biaxial bending. But if only one is not fulfilled, so we must design for biaxial. Okay, let's take a look on this example 5.5. Okay, you can read the detail in the example. I mean, you can read the detail here in page number the question. Okay, the question you can read the detail later. Here, okay, this is the sorry, effective length. From this, okay, from these questions, okay, you can read the detail here. Okay, usually for the design of column involving the biaxial bending, mostly that the column is located here at the corner of the building, where you have a very strong moment. Okay, let's say this is Z and this is Y. Okay, you have column in both Z and Y directions, so you have to check for the biaxial bending. Okay, let's take a look on the example 1.5. Okay, this is the example. This is the specifications, the concrete grade 25, and then the reinforcement 500. Size of B times H is 300 times 300, so it is easy. Okay, you don't have to determine which part of B and which part of H. And then the nominal cover is given as 30 mm. Effective length, okay, about Z axis is 3.5 meter and about Y axis is 3.4 meter, and the slenderness ratio of Z axis is equal to 20.8 and slenderness ratio of y-axis is equal to 23.6, and this is the size of link and size of the main bar, and this is the given value of axial load, and this is the given value of bending moment. This one bend about the z-axis, okay, this one, okay, to 39.5 kN/meter, and this one bend about y-axis is equal to 24.7 kN/meter. So the first, we must determine the value of the imperfection moments, okay, due to the eccentricity. by using these equations, you can refer your module, okay, about the equations, or you can refer back to the this one, this. Okay, you can refer back to our previous example. Okay, the imperfection moment. Okay, this one. Example 5.3, if I'm not mistaken. Okay, how to determine the imperfection moments, the NED times the eccentricity EI. So the eccentricity is equal to L0 over 400. This is the EI. So okay, sorry. So this is the value. Okay, for the along the z-axis, this is the value, and along the y-axis is the value. So the total, the design moment, including the effect of imperfections. So you just add on the given value of 39.5 for z-axis. So you just plus this value 9.19. You got this value for the z-axis, and for the y-axis is 24.7 plus the imperfections moment 8.93. So this is the value, which is the 33.63. And then we check the biaxial bending as mentioned before. Here in this, okay, biaxial bending, we must check the, sorry. Okay, this is the easy. Okay, so we must check this one, E over H. Okay, this one. Okay, EY over H. Sorry, I don't know how to enlarge this slide. Okay, I can adjust. Okay, sorry, I can zoom here. Okay, good. So EY, we need to calculate the value of EY and EZ, okay, which is the eccentricity. Okay, this one. Okay, this is the value of EY and this is the EZ. Okay, because the axial force is not necessarily coincide to the center of the column. It might be a bit offset. Okay, so we can first we calculate this one. Okay, we just, this is the moment. So moment is equal to n times eccentricity. So we want the value of eccentricity now. Eccentricity is equal to moment divided by n. So we got this equation. Okay, or divided by n. So this is the concept. Okay, just use the simple equation from this one. Okay, m is equal to forces times distance, right? Okay, so you want the distance, so moment divided by n. So the moment is this one. Okay, you use the design moment. Okay, the design moment, the latest one. About the z-axis, you use the moment for edy. Okay, like this one. Okay, about the z-axis, you use the moment of edy. Okay, and about the y-axis, you use the moment of z. Okay, just please remember. Okay, and then you got this one. The eccentricity is 32 and 46 mm. Okay, and then you check the value of this one. Okay, the slenderness ratio of both z and y axis. It must be lesser or equal to 2. So you check this one. You just use the value given here. The slenderness ratio is given here. Okay, and then you use this. Okay, just balikkan saja and make sure it less than 2. So we can ignore biaxial bending, but we have to check another one, n. Okay, the word n here means you are still not safe unless you check for all n here. So you must check the second criteria, ey over h divided by ez over b must be lesser than 0.2. But however, when we fill in the relevant value here and here, we got that the value for both criteria is 1.44 and 0.7, which is greater than 0.2. So we need to check for the biaxial bending. Okay. And then for the reinforcement design, okay, this is simple. We design as usual, but later we check, okay, the biaxial bending. And the moment we have to enlarge, okay. So this is the effective depth. D equal to H, the minus C nominal minus link and minus half of the main bar. Okay, 0.5 is main bar over 2. Okay, you can refer to previous video about how to determine, because D and D2, please not to be confused. Okay, so H prime and D prime is equal to 249.5 millimeter. And then, so just simply use this equation. Okay, okay, this one you must check. Okay, the increased moment between this mz over H prime either is greater than my over B prime, or mz over H prime is lesser than the my over B prime, because we want to determine the design moment. Okay, so this one, so you check mz over H prime is equal to mz is this one. Mz is our, this is our mz, okay, 48.69. Okay, medz. Okay, so use this one. Okay, 48.69 divided by the value of our H prime. Okay, our H prime is equal to 249.5 here. So this is the value of mz over H prime, and my over B prime. The my is here as calculated before. This is the medy here. So we use the 33.93. So divide by B prime. So we compare these two value. Okay. So either mz over H prime is greater or lesser than, okay, the mz over H prime is greater than the my over B prime. Okay, in this, okay, you can refer to this okay, page number 202. Okay, we must check. So because we want to determine the equation of a design bending moment, either this equation or these equations. So in our case, we, okay, 195. Okay, this is 195.15, and then another one, this one, okay, this one is equal to 134.79. So it is clear that the mz over H prime is greater than or equal to the my over B prime. So we use this calculation. Mz prime is equal to mz plus beta multiplied by H prime over B prime times the my. If this value is let's say the value here is 110.29, so this one is lesser than this one. So we use the equation, this one, this equation. We use these equations in order to determine our bending moment. But now we focus on this equation, mz prime plus mz equal to mz plus beta. So we use these equations. Okay, we use these equations. And how to determine the value of beta here is this one. Just use simply use beta is equal to 1 minus 1 minus in bracket n divided by BH FCK, and then we multiply the value of BH and FCK first. So the value of n is here, and then the B, the H, and FCK, we got 0.39, and then 1 minus 0.39, the beta is equal to 0.61. So we just use this equation. We just fill in the value of mz, and then the beta here 0.61, and then the H prime and the B prime, and then the my. This one, the my is as calculated before. This is the my. So we got the value of design moment is equal to 69.2 kilonewton meter. So as we learned in example 5.3 and 5.4, we just use we determine the value of D2 and then C nominal plus diameter of link plus diameter of bar over 2. So it's equal to 0.17. We use the chart of 0.2. So from the chart, okay, we must get these two values first. N over BH FCK. So this is the value 0.39. And then the M is over BH square FCK, the value of 0.1. And the M, the value of M here, we use this one, 69.2. Okay. Okay, can you see? Okay, so because the originally given moment is this one, but we do some adjustment, okay, due to the imperfection moment, and then we do the enlargement due to the biaxial bending situations. Okay, so we refer to the column design chart of 0.2. Okay, chart 0.2. You can use this chart for your project later. I hope you practice. And the value of N is 0.39. This one, 0.39 and 0.1. So you can okay, M is 0.1, so you can use this okay, you can you must make sure you use proper ruler. Okay, during your exam, use your ruler properly. This one, okay, 0.1. Okay, and okay, this one 0.1. And then 0. Another value is 0.39. Okay, 0.39. 0.39 is about here. Okay, it's about here. 0.35, 0.4. So 0.39 is about here. So here, what is the value now? The intersection. Can you see? Can somebody tell me the value here? 0 point is between, this is 0.2 and this one is 0.3. So the value here is about here. 0 point?
13.
0 point?
15.
15?
Yeah, 3 or 5.
Okay, let's to 0.25 is here. So let's say it's 0.22. Okay. Okay, so this one, okay, 0.22 here. Okay, the value is 0.22. So you just use these equations. Okay, simple mathematics. Okay, because we want to know the value of AS. This AS required. So you must bring the FY, okay, the BHFCK to the top and FYK to the bottom. You divide it and then you can get the value of AS required is 990 millimeter square, and then you use the 4H25. Okay, 4H25 because you use 25 as the diameter of bar is 25, so you use 45. Maybe you can use 3H25 is greater than this one, if I'm not mistaken. Okay, 3H25 is already greater than 990. However, we must provide at all 4 edges, 1, 2, 3, 4. So it cannot be 3, it must be 4H25. Okay, and then we check the AS minimum and maximum as usual. Make sure that the provided is within the range of minimum and maximum. So then for the link, minimum is the larger of 0.44. Okay, you can refer to our previous video. Is we must select the maximum between the diameter of bar divided by 4 and 6 mm. So 6.2 is between 6.25. Okay, 25 divided by 4. Okay, here, and then 6. So you 6. Okay, so our diameter of link must be larger than 6.25. So as proposed, Let's propose here in the design detail, we propose 8 mm diameter. So we can just use H, and then the laser, this is I believe you can refer to our previous video. The laser off, you must the laser off, okay, the minimum, so we set the minimum 20 times the diameter of bar or the laser dimension of column and 400. So you must select the minimum. So the minimum is 20 times 25 is 500. So minimum here is, so 20 times 25 or 300, or 300 is the dimension of column, okay, and then 400. So the minimum here is you select between 500 here and then 300 and also 400. You select the minimum value. The minimum value now is equal to 300. So you just use 8H300. And at sections, the 250 mm below and above the beam here, which is the critical region, we can okay, here and here, we can simply use the maximum. It shall be 0.6 times 300 equal to 175. So here, so the link here is here at this region. We call it as critical region in earthquake engineering. Okay, and here is H175, and here H8300. We can enlarge the spacing so we can save the cost in terms of steel reinforcement. Okay, that's okay. But however, we have to check. We have to check the criteria of either it's fulfill the biaxial bending requirement or not. So we must check. Okay, this one. Okay, this is the questions. Okay, we must check the situations. Either it fulfill this condition or not. Okay, MEdZ over MRdZ plus, okay, to the power of A, okay, divide by MEdy divide by MRdy to the power of A. It must be lesser than or equal to 1.0. So MRdy is the moment resistance, including the second order moment. MRdy is the resistance. MEdZ is moment designs. Means what? Means MRdy, okay, let's say here, okay, this for these equations, MEd means the design moment or the action, okay, from the action, from the loading, or in simple word, this is the demand. And then the MRd is the either Y or Z. This the resistance moment, okay, or the capacity, or in a simple word, this one is known as the supply. Okay, so the supply must be greater than the demand. Okay, this is the action, okay, from the loading, and this is the demand from the cross sections, okay, from the concrete and the steel reinforcement. Okay, so we must check. Okay, this is okay, for overall is 4H25, and then for the along the Z axis this is symmetrical or similar. So the AS is similar. So we must calculate, okay, the both directions. We have to use chart 0.2. This is what we call as reverse actions. So we check the N is equal to 0.39 as we calculated before. Okay, 0.39. So for the Z-axis, okay, we use these equations. Be careful with this one. Okay, AS FYK divided by BHFCK. Okay, from these equations, okay, from this one, okay, the AS here is the AS required. Okay, but for checking now we we must input this one as the as provided. That's the difference. Okay, so as provided is equal to here 1964. So 1964, okay, 1964 multiplied by FYK is here 500 divide by the BHFCK. So 300, 325. So 300 times 300 times 25. So it's equal to 0.44. So we open the column chart here. Okay, the column chart. Okay, I will. Okay, 0.39 is still 0.39 here. The value is here 0.39, and then the calculated ASFYK is 0.44 here. So you must go to here. 0.44 is, okay, let me enlarge this chart first. 0.44 is here. This is 0.4. Sorry, I used. Okay, this is 0.4, this is 0.5. So 0.45 is here. So let's say here, so the value is 0.44. Okay, lesser. Let's see here. This one. And then the 0.39 here. We drag it here. We find the intersections. Okay, we find the intersections, which is approximately located here. Okay, so this is how to use the chart, class. Okay, you must be careful. Okay, so and then we bring it here. One. Okay, let's say it's 0.15, the value of MBHFCK. So it's 0.15. Okay, clear? 0.15. Okay, I hope you are clear of how to get this value 0.15. So we use these equations. We want to know the value of moment now. So 0.15. So M over BH square FCK equal to 0.15. We want to know the moment. So we bring it, okay, to the top times BH square FCK. So this is the calculation and this is the value. This is the supply. Okay, the supply is 101.25 kN, and then the demand is equal to this one. Yes, 69.2. Okay, so supply is greater than the demand. So for the y-axis, it's a similar process, so the similar value. And then the NRD, so this one, this is 667. Okay, 667 because this one is, okay, NRD is equal to ACFCD plus ASFYD. So FCD, you must always remember FCD is equal to 0.667 FCK, and then FYD is equal to 0.87 FYK. So you just multiply here. The value is here, and then here for AC. So this is the N, and then this one is important in order to calculate the moment. Okay, the A. Okay, so you can get the value of A here, 0.49 from this table. The value of A, okay, you can use the interpolations to get the value of A. Okay, you guys, from this table, interpolations, and then you